NASA has announced the discovery of a new Earth-sized planet orbiting its star's optimistic habitable zone.
The James Webb Space Telescope has revolutionized our understanding of the cosmos since its launch, delivering unprecedented insights and breathtaking images of the universe's most enigmatic phenomena. However, some observations have been more alarming than others. Famous physicist Brian Cox has confirmed that the James Webb Telescope has just detected a sudden 250% increase in Betelgeuse's brightness. So what does this mean? Will the star go supernova? And how will that affect our planet? Well, there is a lot to unpack, so let's get started with some context. Betelgeuse, a star at the brisk of a supernova. The night sky has always been more than just a collection of stars. Travelers have long used the canvas of stars and galaxies to map their paths. Lovers have pointed to the twinkling lights and claimed them as witnesses to their enduring bond. And astute observers have noted that the landscape is a living chronicle of the universe's history. However, one star has captured the human imagination like no other: Betelgeuse. Set within the iconic outline of Orion, this red supergiant is a beacon in the sky, outshining its stellar companions with an intensity that commands attention. Betelgeuse resides roughly 650 light-years away from our planet, a distance so immense that it transcends the limits of our comprehension. It roughly equals an astonishing 6 quadrillion, 150 trillion, and 650 billion kilometers. So, how come this distant celestial body commands such attention? Why the fascination? Well, Betelgeuse is not just a star. It is a cosmic titan, a red supergiant, one of the most massive stars known to science. To put its size into perspective, if this giant star were placed at the center of our solar system, its outer layers would extend beyond the orbit of Jupiter. It dwarfs our sun in both size and grandeur. But there's one more thing about the star that makes it so unique. Unlike the sun, this star exhibits dramatic changes in brightness. Betelgeuse has long puzzled scientists who have dedicated their lives to studying it. However, the true wonder of Betelgeuse lies not only in its size or its fiery red hue, but in the fact that observing it is like looking back through the corridors of time. The light we see today from Betelgeuse set out on its journey over 600 years ago, during an era when the Renaissance was just beginning to awaken in Europe. This delay, a result of light's finite speed, means that every flicker and pulse we witness is a message from the distant past, a glimpse into an era when humanity was still in its infancy of understanding the cosmos. Each observation we make of Betelgeuse is a direct connection to that distant epoch. What we observed recently, however, sent shockwaves throughout the scientific community. Recent observations and findings. Recently, the James Webb Space Telescope detected a significant increase in Betelgeuse's brightness. This brightening phase started earlier in 2023, when the star began to shine even more intensely than its standard peak luminosity. This sudden increase is particularly intriguing because Betelgeuse had previously experienced a major dimming event from late 2019 to early 2020, known as the Great Dimming, which puzzled astronomers worldwide. The current rise in brightness might be an indicator of significant internal changes within the star, possibly linked to the processes that precede a supernova explosion. Betelgeuse's current brightening stands in stark contrast to its behavior during the recent dimming event. During that period, Betelgeuse's brightness dropped significantly, reaching its lowest level in recorded history. This extraordinary phenomenon unfolded between October 2019 and early 2020, presenting a perplexing puzzle that compelled both astronomers and enthusiastic stargazers to seek answers. Dubbed the Great Dimming, this event marked a significant deviation from Betelgeuse's well-established brightness patterns, capturing the attention of those who often look to the night sky for celestial wonders. For observers, the changes in Betelgeuse's luminosity were striking, becoming apparent even to the casual eye. This shift raised compelling questions regarding the star's current state and future trajectory, particularly its potential evolution toward a supernova explosion, a fate long speculated upon for red supergiants like Betelgeuse. While variability in brightness is characteristic of such stars, the degree of dimming observed during this event was unprecedented, stirring a sense of urgency among astronomers. As the news of this dimming phenomenon spread, a multitude of theories emerged to explain it. One prominent hypothesis suggested that a significant outflow of gas and dust from Betelgeuse's surface might have obscured its light, creating the illusion of a dimming star. This image painted a picture of a celestial giant undergoing turmoil as it shed its outer layers in a dramatic display. Alternatively, some researchers considered the possibility of a cooler region on the star's surface, a so-called cool spot, contributing to the dimming. In response to these uncertainties, a collaborative effort among scientists led by Kenichi Nomoto from the Kavli Institute for the Physics and Mathematics of the Universe sought to shed light on Betelgeuse's enigmatic behavior. Their investigations revealed surprising conclusions. Betelgeuse might be smaller and closer to Earth than earlier estimates suggested. They proposed that a cloud of dust was indeed responsible for the dimming. At the same time, another group of astronomers, guided by Hideyuki Sayo from Tohoku University, examined Betelgeuse's rhythmic pulsations, identifying a cyclic pattern of expansion and contraction occurring roughly every 420 days. This cyclical behavior highlights the star's unique nature and emphasizes the complexities of its luminosity changes. As the great dimming event gradually receded and Betelgeuse's brightness returned to its normal levels, it left behind a trail of questions that would continue to intrigue astronomers. One of the more puzzling aspects involved a recorded drop in temperature during the dimming phase. Research indicated phenomena similar to sunspots on our sun, dubbed star spots, may have played a role in this temperature fluctuation. These cooler regions on Betelgeuse's surface can influence its overall radiative output, similar to how sunspots affect solar luminosity. The interplay of magnetic fields and the presence of star spots could have temporarily obstructed radiation from the star's core, contributing to the observed temperature drop during the dimming period. The implications of these findings extend far beyond Betelgeuse itself, offering critical insights into the behavior of red giants, which are crucial for the synthesis of heavier elements in the universe. As these stellar behemoths produce elements heavier than helium, understanding their variability and the factors influencing their brightness is vital to comprehending the chemical evolution of the cosmos. Betelgeuse's dimming event not only sparked vibrant discussions among astronomers, but also emphasized the complexity of stellar behavior. As new revelations emerge regarding this remarkable red supergiant, they promise to reshape our understanding of the life cycle of massive stars and their roles in the cosmic web. Broader implications for astronomy. Understanding stellar life cycles and the phenomena associated with supernova precursors is essential in astrophysics. The life cycle of a star is fundamentally determined by its mass. Low-mass stars, like the Sun, transition through various stages, culminating in the formation of a white dwarf after shedding their outer layers. In contrast, high-mass stars evolve into red supergiants, undergo multiple stages of nuclear fusion, and ultimately end in catastrophic supernova explosions, leaving behind neutron stars or black holes. Supernovae play a crucial role in enriching the interstellar medium with heavy elements. These elements are vital for the formation of new stars and planets. The impact of these processes significantly influences galaxy dynamics. Supernovae can trigger star formation in nearby regions by compressing gas and dust, while the energy released can also disrupt existing structures within galaxies. Continuous monitoring of stellar activities and the use of diverse observational tools, such as space telescopes and ground-based observatories, are crucial for enhancing our understanding of these processes. For example, we know that Betelgeuse plays a significant role in cosmic dust production. The mechanisms behind dust formation in such stars involve various processes, including the cooling of gas and the condensation of heavy elements. This dust contributes to the formation of new stars and planets. Studying Betelgeuse and similar stars can provide insights into how stellar winds and material ejection affect the circumstellar medium, creating conditions conducive to star and planet formation. Moreover, the interactions between ejected material and the circumstellar medium produce observable phenomena. such as nebulae and variable brightness in nearby stars, which offer valuable data on stellar evolution. Naturally, research into these interactions is essential for understanding the life cycle of stars and the broader processes that shape our universe. But how do we do it? Observational advantages of the James Webb Space Telescope. The James Webb Space Telescope, or JWS for short, has transformed our understanding of the universe through its advanced observational capabilities. Launched on December 25, 2021, this powerful space observatory offers unprecedented insights into cosmic phenomena by employing cutting-edge technologies and capturing infrared wavelengths. The JWST can peer through cosmic dust, observe distant galaxies, and study the atmospheres of exoplanets with remarkable clarity, vastly surpassing the observational limits of its predecessor, the Hubble Space Telescope. The combination of its positioning in space, its advanced spectroscopic capabilities, and its ability to operate in the infrared spectrum allows JWST to explore the universe's earliest epochs, providing valuable data on the formation of stars, galaxies, and planetary systems. All of this was not achieved overnight, though. For centuries, humanity relied on ground-based telescopes to explore the cosmos. The first significant advances in this field were made in the 17th century, notably with Galileo Galilei's use of a refracting telescope. His observations of celestial bodies, including the moons of Jupiter and the phases of Venus, challenged the geocentric model of the universe and laid the groundwork for modern astronomy. While he himself faced persecution for his views, which were deemed heretical by the religious establishment of the time, the subject itself took off and contributed immensely to our collective understanding of the cosmos. Other notable figures included Sir Isaac Newton, who built the first reflecting telescope in 1668, allowing for clearer images by using mirrors instead of lenses. Throughout the 19th century, ground-based observations led to significant discoveries, such as the identification of the composition of stars through spectroscopy. The work of astronomers like William Huggins and others in this period demonstrated that stars were primarily composed of hydrogen and helium. Despite these advancements, ground-based telescopes faced significant limitations due to atmospheric interference. The Earth's atmosphere distorts light, making it challenging to obtain clear and consistent observations. This limitation sparked a desire for instruments that could operate above the atmosphere, free from such distortions. The launch of the Hubble Space Telescope in 1990 marked a watershed moment in astronomical observation. Hubble was developed to overcome the limitations of ground-based telescopes by placing a powerful observatory in low Earth orbit. With a primary mirror measuring 2.4 meters in diameter, Hubble's design aimed to provide unprecedented clarity and resolution. Equipped with a suite of advanced instruments, including cameras and spectrographs, it could observe across various wavelengths, from ultraviolet to near-infrared. Hubble's contributions to astrophysics have been monumental. It has provided insights into the rate of expansion of the universe, contributing to the discovery of dark energy. Its observations of distant galaxies have revealed a diverse range of structures and formations, while its stunning images of nebulae, such as the Pillars of Creation in the Eagle Nebula, have captivated both scientists and the public alike. However, Hubble was not without its challenges. Shortly after its launch, a significant flaw in its mirror was discovered, leading to distorted images. This setback was addressed with a servicing mission in 1993, which corrected the optical issue. Subsequent servicing missions allowed for upgrades to Hubble's instruments, extending its operational life and enhancing its capabilities. However, as the scientific community began to explore further and deeper into the universe, the need for a more advanced telescope became evident. The James Webb Space Telescope, or JWST, launched in December 2021, was developed to explore the universe in greater detail than ever before. Unlike Hubble, JWST focuses primarily on infrared observations, allowing it to peer through dust and gas clouds that obscure visible light. JWST features a large primary mirror that spans 6.5 meters in diameter, composed of 18 hexagonal segments. This design enables it to gather more light than Hubble and offers greater sensitivity to faint objects. Its instruments include the Near-Infrared Camera, or NIRCam, the Mid-Infrared Instrument, or MIRI, and the Near-Infrared Spectrograph, or NIRSpec, all of which allow it to explore a wide range of astronomical phenomena. The JWST's objectives include investigating the formation of stars and galaxies, studying the atmospheres of exoplanets, and exploring the early universe's history. Its ability to observe distant galaxies means it can capture light from when the universe was merely a fraction of its current age, shedding light on cosmic evolution. Moreover, JWST's position at the second Lagrange point, located about 1.5 million kilometers from Earth, allows it to maintain a stable environment for observations while being shielded from the heat and light of our planet. This unique location, coupled with its sophisticated cooling systems, enables JWST to detect the faintest infrared signals, revealing a universe rich in details. One of the most significant advantages of the James Webb Space Telescope is its ability to penetrate dust and gas that obscure visible light, enabling astronomers to observe celestial objects that have long eluded study. This feature is especially crucial for red supergiants like Betelgeuse, which are known to produce substantial amounts of dust during their later evolutionary stages. The infrared instruments aboard JWST can capture this elusive material, providing enhanced observations that yield clearer insights into the behavior of these massive stars and the processes involved in their material ejection. By using infrared wavelengths, JWST not only reveals the dynamics of red supergiants, but also impacts the study of other stars at various evolutionary phases. This capability allows astronomers to explore protostars, which are still forming and shrouded in dust, as well as the remnants of supernovae, where newly formed elements are dispersed into the surrounding medium. The ability of JWST to observe the cosmos in infrared light opens new avenues for understanding stellar life cycles. By analyzing how dust affects light and gas interactions around these stars, astronomers can gain a deeper understanding of how stellar winds and pulsations contribute to cosmic dust production, influencing future star and planet formation. The JWST's observations promise to deepen our comprehension of the life cycle of stars and the intricate dynamics at play in stellar evolution, ultimately shedding light on the fundamental processes that govern the formation and evolution of galaxies. With that cleared up, let's move on to the implications of our observations. Was the Great Dimming related to an impending supernova? And what about the recent brightness boost? The connection between dimming and supernova? A star's dimming relates to various stages of its life cycle, with intriguing implications for the possibility of a supernova. While dimming may result from natural variability, understanding its connection to supernova events requires delving into the intricacies of stellar evolution and observational astronomy. A star's brightness can fluctuate due to a variety of factors. This can include intrinsic variability, such as pulsations or external influences, like the passage of a planet or a dust cloud. A key example is the behavior observed in red supergiants, massive stars nearing the end of their life cycles. These stars, like Betelgeuse, can exhibit fluctuations in brightness, characterized by periodic dimming and brightening. The mechanisms behind these changes are complex, often involving dynamic processes in the star's outer layers, such as convection and pulsations driven by the star's nuclear processes. Red supergiants represent a significant phase in the life of massive stars, occurring after they have exhausted their hydrogen fuel and transition to burning heavier elements. As they evolve, these stars can experience changes in luminosity due to convection currents, thermal pulsations, and mass loss through stellar winds. This variability raises questions about the predictability of supernova events. Historically, astronomers have monitored red supergiants for precursors to supernova explosions. The reasoning is that as these massive stars near the end of their nuclear fusion processes, they may exhibit signs of instability, which could foreshadow a catastrophic collapse in subsequent supernova. However, predicting a supernova based on dimming events is fraught with uncertainty. Not every instance of brightness fluctuation in a red supergiant signifies an imminent explosion. For example, Antares is a red supergiant, and undergo significant changes in brightness over time. These fluctuations can sometimes be dramatic, leading to speculation about its stability and the possibility of a supernova. However, despite its varying luminosity, Antares has not yet shown any signs that indicate an imminent explosion. The changes in brightness in stars like Antares are often due to natural variations in their outer layers, such as pulsations or large convective cells that move heat within the star. These factors can cause the star to expand or contract slightly, affecting its brightness. This process is common among red supergiants and doesn't necessarily mean that a supernova is on the horizon. The challenge of predicting a supernova based on dimming events is further complicated by our limited understanding of the mechanisms driving stellar evolution. While there are models that describe the life cycles of massive stars, many of these models require adjustments as new observational data emerge. For instance, studies of red supergiants reveal that their behaviors can vary significantly from one star to another, making it difficult to generalize predictions about dimming events and supernova occurrences. Moreover, factors such as magnetic fields and internal oscillations within the star may also influence its brightness. Some researchers have proposed that the presence of magnetic fields could play a role in shaping the convection patterns and mass ejection processes in red supergiants. This, in turn, can affect their luminosity. If a dimming event were indeed related to an impending supernova, it would have significant implications for our understanding of stellar evolution and cosmic processes. Understanding such a relationship could also enhance our observational strategies. However, for the sake of argument, let's assume that the great dimming observed in Betelgeuse was somehow tied to an impending supernova event. Could it then be that Betelgeuse just returned from the brink of a supernova? Is such a phenomenon even plausible? Unfortunately, the scientific consensus is a firm no. Once a massive star like Betelgeuse approaches the threshold of a supernova, it is already in a critical phase of its life cycle. Beyond this point, any sort of revival is simply and utterly impossible. Massive stars like Betelgeuse begin their journey as main sequence stars where the core's nuclear fusion process converts hydrogen into helium. This fusion reaction generates the energy needed to counteract gravitational forces, thus maintaining the star's stability. As the hydrogen in the core depletes, the core begins to contract under its own gravity. This contraction increases the core's temperature, allowing helium fusion to commence. The star transitions through various phases, fusing heavier elements like carbon, oxygen, and ultimately iron. This sequence of fusion processes is crucial, as each stage transforms the star's structure and energy output, dictating its eventual fate. The last on the list, iron, can't yield energy through fusion. Naturally, once a star's core primarily consists of iron, it can no longer sustain itself against gravitational collapse. Instead, the iron core accumulates mass until it reaches a critical threshold known as the Chandrasekhar limit, which is approximately 1.4 times the mass of the Sun or more. Beyond this limit, the core's pressure cannot counterbalance gravity, leading to a swift and catastrophic collapse known as a supernova. The energy unleashed during this event is so immense that it can temporarily outshine entire galaxies. The remnants of this explosion may leave behind a neutron star, or in the case of extremely massive stars, collapse further to form a black hole. So if Betelgeuse were on the verge of a supernova, the progression toward that event would be irreversible. While the recent dimming episodes have raised questions and fueled speculation about the star's fate, any return to normal brightness would imply that the dimming was not associated with impending collapse. Instead, these fluctuations in brightness could stem from other, less catastrophic processes. At least this is what conventional wisdom tells us. So, what is actually going on? A research team from France's Université Côte d'Azur employed the advanced Matisse instrument on the European Southern Observatory's Very Large Telescope Interferometer, located in northern Chile, to understand the Great Dimming. Over a crucial observational period spanning from December 2018 to December 2020, they captured high-resolution images of Betelgeuse, allowing them to closely monitor its behavior during the dimming event. In October 2023, this team presented a groundbreaking theory that proposed a veil of dust, described as a ghostly shroud, was responsible for obscuring Betelgeuse's luminosity from our view. This dust, identified as being composed primarily of silicon monoxide, was not simply an external occurrence, but rather material expelled by the star itself. These findings resonate with earlier theories, notably a 2021 study that posited Betelgeuse had undergone a celestial burp, where gas was expelled from the surface due to a sharp decrease in temperature. This expulsion of material resulted in the formation of solid dust particles that enveloped the star, casting it in shadow. Such dust clouds play a significant role in stellar evolution and can eventually contribute to the formation of new star systems. The interplay between massive stars like Betelgeuse and their surrounding environments is crucial for understanding stellar life cycles and galactic ecology. As these stars evolve and shed material, they enrich the interstellar medium, providing the building blocks for future generations of stars and potentially even planetary systems. We can also understand the recent brightness boost in this context. Since we now know that the Great Dimming was due to a large cloud of gas expelled by the star, which then condensed into dust, we can extend the hypothesis to understand this recent anomaly too. As Betelgeuse's pulsations continued, the star's temperature increased, leading to the dispersal of the dust cloud and a subsequent rebound in brightness. The recent brightening is thus simply a return to normal levels following the dispersal of that dust cloud. But now comes the million-dollar question. Will we witness a supernova anytime soon? Well, before we dive into the answer, let's get one thing cleared up first. The Great Dimming, the dust cloud, the brightness boost, and everything in between. None of these dramatic events are unfolding in real time. The light we observed during this period in 2019 actually reflects a state of Betelgeuse that occurred over 600 years ago. So, if we were to witness a Betelgeuse supernova tomorrow, it would have actually happened back in the 15th century. The actual question is then, has the star already undergone a supernova? Well, the unpredictable nature of stellar life cycles means that while we might one day witness Betelgeuse go supernova, pinpointing the exact timing remains elusive. Many researchers hypothesize that the star continues to reside within the helium-burning phase of its life cycle. This perspective is bolstered by studies from Hungary's Konkoly Observatory, where astronomers, including Kenichi Nomoto of the Kavli Institute for the Physics and Mathematics of the Universe, have analyzed the star's behavior. However, an alternative theory from Dr. Hideyuki Sayo presents a different perspective. They claim that Betelgeuse might already be in its carbon-burning phase. If true, the star could implode within decades rather than thousands of years later. This drastic difference in predicted timelines adds an electrifying twist to our understanding of Betelgeuse. The star is nothing short of a cosmic ticking time bomb. Regardless of the differing theories, one fact remains undeniable. Betelgeuse is on a trajectory to become the Milky Way's next supernova spectacle. When it eventually reaches the end of its stellar life, the event will be nothing short of transformative for the night sky. A red supergiant's explosion is among the most energetic phenomena in the universe, and the impending supernova will unleash a torrent of neutrinos that will arrive on Earth before the visible light of the explosion. The initial explosion will likely result in an unprecedented burst of brightness, with Betelgeuse outshining the moon and potentially becoming visible during the daytime. As the supernova progresses over the following days and weeks, the event will undergo fascinating changes in color and brightness. This evolving spectacle will offer a rare opportunity to witness the majestic power of nature firsthand. In the aftermath, Betelgeuse will leave behind a stunning celestial masterpiece. The star may either collapse into a neutron star or a black hole. Regardless of its fate, the spectacle of Betelgeuse's supernova will stand as a unique and monumental event in the collective memory of humanity, resonating for generations to come. As we find ourselves poised on the brink of witnessing Betelgeuse's supernova explosion, we stand at a remarkable juncture in cosmic history. This stellar event promises to be a pivotal moment, not just for astronomy, but for our understanding of the life cycles of stars. The fate of Betelgeuse hangs in the balance. But what will become of it? Well, if Betelgeuse's core collapses, the remnants will coalesce into a neutron star, a strikingly dense object that compresses approximately 1.4 to 3 times the mass of our Sun into a sphere roughly 12 miles or 20 kilometers in diameter. Neutron stars are composed predominantly of neutrons, which are subatomic particles that reside in atomic nuclei. These stars exhibit incredibly strong gravitational and magnetic fields. They are so dense that a mere teaspoon of neutron star material would weigh about as much as an elephant. However, if Betelgeuse's core reaches sufficient mass, it could collapse into a black hole, an object with gravity so intense that not even light can escape its grasp. This is where the black holes get their name from. These celestial objects do not emit any detectable radiation and are invisible against the backdrop of space. Studying Betelgeuse and its impending supernova is not merely an exercise in astronomical observation. It provides critical insights into the fundamental processes that dictate stellar evolution. While the exact timing of Betelgeuse's explosion remains uncertain, it underscores the vast mysteries still waiting to be unveiled in the cosmos. In this grand celestial theater, patience is essential. Though unpredictable, Betelgeuse reminds us that the universe is replete with enigmas and wonders, each waiting to be discovered. As we keep our gaze fixed on the night sky, we anticipate a cosmic spectacle that promises to transcend time and space, etching itself into the annals of human history. But for now, Betelgeuse stands strong at its position in the night sky, with its magnificence glowing brightly and the dimming event past it. One day, this star, like all others like it, will all but vanish. Until that fateful moment, we can gaze peacefully at the night sky, marveling at the celestial icon that puzzled and amazed countless people before us. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.